Hello, so I'm going to show you how to prepare sand samples for the direct shear test. So remember, direct shear test, we have three parts. So first we need to reconstitute the sand samples. The second part will be consolidation. And the third part will be actually shearing the sand specimens. So this is the very first part on how to prepare or reconstitute a sand sample. And it first come with the direct shear box. And the direct shear box has the box can break into two parts. So this is a direct shear box. You have an upper part, and you also have a lower part. And there's also a couple of discs come with it. So when you assemble the boxes, you have the two go on top of each other, and then you have all these pieces. So first you have a bottom disc right here. So you realize you have all this small holes on the disc is for water drinkage. So this first of all go into the bottoms, and then you have a brass disc. So this is pretty much is kind of like a stone for you to prevent the sand particles go outside the box. So it should be a material, in this case a brass, sometimes could be porous stones, that to prevent the soil. Sometimes you have very fine soils, even you are testing on sand, you could have some fine particles there coming out from the box. So you have the bottom part, and then the next we will reconstitute the or we will puree the sand samples into this box. After that, we have the same part, the disc, and also another triple disc go on top. And to assemble this two boxes together, we have some pins. So we have some pins here to make sure the boxes are perfectly aligned. So those pins will go into the boxes such that the boxes now is 100% well aligned. So now we finished assembling the box, and it's ready for sand purifications. So what we'll be testing on will be octava sand. It's a white, rounded, kind of like a sifted test that has a poorly graded gradation curve. So which means you have a standardized particle size. So next, what we do, we use a funnel to purify sand into our direct shear box, and we want to measure the mass. So we want to keep track with the mass going into the box, such that we know the mass, and we can measure the volumes. And the volumes can be calculated by measuring using a caliper. So we will get a caliper. So we can use the caliper. So this is a caliper to measure the diameters, the inside diameters of the openings. So we know the diameters. So the next thing is we will weight the boat here with the sand. So we know the mass of the boat plus the sand before we put the soils into our shear box. So next, with the funnel, in the sand in the funnels, and then we will start prove it into the box. As the way it goes, sand will goes in, and we want to keep the drop height from the funnel. Actually, the drop height means like from the tip of the funnel to the sand surface that go down here. We want to keep this distance as minimal as possible, such that we can create a loose structure. And just for you to see it. So now you see this is the drop height, and we want to keep this drop height as small as possible, in fact. So we keep proving our sand samples. We will move this in a circular patterns until we fill up the box. Then we can level this out. So after this has been leveled out, make sure all the soils go into the box, nothing go outside our shear box. Then this is our sand specimens that we're going to test on. And the other fact is, after we finish the purifications, we will measure the mass again. So we measure the mass before purifications, and also we measure the mass after purifications. And the latch between the two measurements will be the mass inside, the amount of sand in terms of mass inside the shear box. So after the purifications, and then we put on our top bars disc. And then we put on also another triple disc. So now if we do everything perfectly in terms of the height of the specimens, remember we want to find out the volume of the specimens. We know the diameters. We also want the height of the specimens. And what we will do, we will before we start, we will also measure the thickness of the toolbox. So the thickness of the toolbox plus any additionals well, maybe if we have proved in a sense that the sand right at the rim, then the thickness of the box will represent the height of the specimens. Or the other way we do it is if the sand end up to be too tall and to be too height, we need to correct for the height with measuring the thickness of the disc that you have. So with this, then we kind of measure the thickness of the disc, and then we will also measure the height from the triple disc to the bottoms. In that case, if we measure the height of the triple disc, so the caliper, the other end, there's two ways to use this caliper. First, the thickness can be the measurements can be defined between these 2 points here, and the other hand can also define by these 2 points there. And now, after you have knowing the height of this the box and also the height of the two discs, and now you have this measurements minus the thickness of the box plus the dual disc. So the difference will be the additional amount of sand that may be stick out. Or if this the sand specimen is too short, then what you would do is measure from the rim to the top of the disc. Then you can also measure you can also know the correction height of the specimens. For more information, I will talk about it in my lecture slides. So now that's your specimens with the top cap put on that. So this is a top cap with the direct shear machines. That case, then we will be ready for the next steps. Okay, let's look at this direct shear machines together, and let's talk about how this device works. Remember, we just finished reconstituting our soil samples. So the box that we put together now will go here. So the middle part of the device is what we call this the water bath. So this water bath is the place where we put in our soil specimens. And we call it water bath because it has the it gives us the possibility of fill this up with water, such that you can saturate the soil samples if you want. But today we will be just running dry tests with dry sand. So this is the middle part, and this middle part is connected with the with two ends. So the left hand side is kind of like go with a motor. So if we turn on the motor, the whole thing will push the water bath with the soil samples to the right hand side. And what we have at the right hand side is a load cell. So this is a load cell here, which for us to measure the loading. And it's kind of like a dead end. So what it does is when we push the whole thing to this size, and so this water bath, you have water at the bottom, so you can move. So when this one to move to the right hand side, and you'll be stopped right there because this end is connected to the way to stop there. So you want to move but being stopped, but the resistance where it comes from is from the soil, because like for this water bath, what happened is it has the bottom part try to connecting with the water base in the bottom that can move, but the top is being stopped. So if you can look inside right there, so this is the connections where the top part, now the top of the shear box being stopped right there, but the bottom part is hard to see. You pretty much need to take off the whole thing to see the water. So the bottom part of the shear box can move, but the bottom part of the shear box can move, but the top part being stopped. So what it is resisting the movement now is the interface, the sand interface between the top and bottom part of the box. So this is how the direct shear machines to work. Okay, so we finished preparing our soil samples, and we finished our first steps, our first phase. Now we getting to our second phase, which is the consolidation part. Remember, we have three phases: soil specimen reconstitutions, which we finished by preparing the sand samples inside the shear box. The second part now is the vertical consolidations. So these machines have like a vertical components, and also a shear, which is the horizontal components. So now we're at the second phase, which deal with the vertical consolidations. And the third phase after this will be the shearing phase, which is the horizontal component. So now at the second phase, second components, what we do is we apply a dead weight, a vertical loading to our soil samples. Remember the Moore-Coulomb theory, the soil strength is highly depends on the vertical stress. And the vertical loading we apply on that will be calculated based on the stress level we want to get to. So in your data given to you for this lab, and you need to write a lab report about it, you have a couple different like vertical stress, like 15 psi, 45 psi, 60 and 75 psi. So those are the stress you applied on your soil samples. And we need to calculate the vertical loading representing the stress. For example, if you have 15 psi, if you have the 15 psi stands for pound per inch square, you multiply by the area of the soil samples. So that's why at the beginning it's important for us to measure the dimensions of the inside diameters of the shear box. That gives you the diameters or the area of the soil samples. So you have the 15 psi times the area that gives you a loading that you need to put on your soil samples. And imagine it's like in order to establish the Morgan envelope, we need 4 tests. So on the Google Sheet, we give you 4 test results, 4 test data too, which means this the direct shear test need to be run 4 times at different like a vertical stress level, 15, 45, 60, and 75 for a lap. In practice, the stress level that you target for will depends on your project. So you want to your stress that goes test in the lab is a good representation of what happened in the field. But anyways, after we know the loading that we need to put on, now is applying the loading to our soil samples. So for this setups, you will see that's like a loading frame. This is a vertical loading frame right here. And also in the bottoms, those there will be some hanger for you to place the weight. So first we apply the loading frame. So the loading frame, we put on this, and then we start assigning a weight to our soil samples. And this loading frame has a weight of 4.75 kilogram. So the weight of this loading frame is 4.75 kilograms. So that's the weight for now. We're adding on it. And for this loading frame, it has 2 parts in the bottom for these machines. So this vertical alignment is connecting right to your soil samples. So this is a 1-to-1 loading frame. So any weight I put here will be exactly equals to the weight I put on the soil samples. So if I put 1 pound here, there will be 1 pound adding to the soil. And this is kind of like a loading frame that gives you mechanisms that give you a 1-to-10 ratios, which means if I put 1 pound at the other side, it will become 10 pounds because this is like a lever system. So give you a ratio of 1-to-10. So 1 pound here, 10 pounds will be on the soil samples. So for example, if I want to apply, this is kind of like a 10 pounds loading block. If I put it here, then it becomes 100 pounds on the soil samples. So depends on the loading you need to get to, you will have different assigned weight you need to work on. And the other part is to capture the deformations of your soil. Then we also have a vertical gauge, like a dial gauge, connect to your loading frame. So there will be another like video to instruct you or to show you how to read a dial gauge. But this dial gauge is supposed to be installed to be there. So once we put on our vertical alignments, we'll put on the dial gauge, and the next steps will be adding the weight that we want. So once we add the weight we want, you will see from the dial gauge that your reading will be changing. So that represents the amount of deformations or the consolidations that happens because of the weight that we add on. And you could also imagine, you will know that, you imagine that the more weighting you add on, the larger deformations there will be. Okay, so after the second phase of the vertical consolidations, now we are ready to get to our third phase, which is the shearing phase. So in this stage, we focus on the horizontal alignments. And before we start this phase, there's a very important safety steps that we need to take care of, is removing this 2 pins. So this, remember the pins that we set up at our very first phase when we prepare the soil samples, this is for ensuring the vertical alignments of the toolbox. But now we don't need any more. If we still have those 2 pins on, when we are loading the soil samples, you will be shearing the pins, but not shearing the sand samples. So once we remove the 2 pins, then we are ready to start our loading phase. And in the horizontal alignments, you will realize that in fact there's 2 dial gauge right there. First is the one that come with the low gauge. So this is the low cell for the dial gauge for the low cells. So when wheel is low on it, you realize what I'm doing is pushing the low gauge, and then you will see there's a deformations. So you will pick up the loading that we have, and this dial gauge have a calibration factors, which is 1 dial readings equals 0.2 pounds. So it has a precisions that you see like every like a small divisions in the outside readings corresponding to 0.2 pounds. So that just come from the stiffness of our rings. So this is kind of like a very old school dial gauge type of low cell. So this is for measuring the resistance from the sand. And there's another dial gauge go from here connected to the water bath. So this is the dial gauge for you to pick up the horizontal displacements, because the whole mechanism is when we turn this crank here, and the whole thing will move. So if I'm turning the crank, so which is making the whole thing moving to the right hand side, then we will pick up the displacements there. So while I'm moving, the low gauge will change tiny a little bit too. But in the long terms, once the soil samples being engaged, then you will pick up the readings from the dial gauge too. So this is the basic setup. So when the test gets started, what happens is when we're doing this in the lab, there'll be 1 student cranking the motor at a very slow and constant speed. And then there's another like 3 more students will be take care of reading those 3 gauges. And maybe every period of time, maybe every 10 seconds, there'll be a timer, say read, then the 3 students will read down the reading of the dial gauge. And the data will be, all of them will be available on a Google Sheet. So your task will be take those data, and then like I come up with a stress strain curve representing the shear resistance picked up from the low cell with the displacements. So you're reading the displacement here, and also you're reading the loading there. That should give you a stress strain curve. Your lab report also requires you to plot out the vertical displacement change with the vertical displacements, which means when we're shearing these machines, when we're in the shearing phase, when we're shearing this, what is the change of the vertical displacements along the times. So that will be also required in your lab report. So that's how we interpret data. So we keep like cranking this until we are getting about 10 to 20% of shear strain. So shear strain is defined by the horizontal displacements divided by the height of the specimens. So when we get to about 10 to 20% of shear strength, or like your stress strain curve got level out, then that's the part that we finished the test.